They call them lakes, but if you stood on their shores without a map, you would think you were looking at the ocean. The horizon disappears, waves rise taller than houses, storms sink ships. Lake Superior alone is large enough to swallow entire weather systems. Together, the Great Lakes hold nearly one-fifth of all the liquid freshwater on Earth. This is not a chain of ponds, it is an inland ocean. And oceans do not freeze overnight. They store summer heat for months. They circulate. They resist the first bite of winter. Water this vast does not surrender quickly. But one winter something changed. Cold settled in and refused to lift. Winds stripped warmth from the surface, faster than it could rise from below. Dark water began to dull. Harbors stiffened. Shipping routes narrowed. From space, white spread across what had once looked like open ocean. Ice coverage climbed toward levels not seen in decades. 6 quadrillion gallons of fresh water began to slow, not all at once, but enough to feel impossible. So, what does it take to quiet an inland sea? How much cold is required to overcome something this large? What happens beneath the surface when motion itself begins to hesitate? Tonight, we return to the season when the Great Lakes stopped behaving like lakes and began to resemble a frozen ocean. But before we begin, if you find comfort in these quiet journeys through science and story, it would mean the world to me if you gave this video a gentle like and maybe tapped subscribe. It helps more curious minds like you find their way to this peaceful little corner of the internet. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? I love seeing how far across the world these soft explorations travel. So now take a deep breath, let your body relax, and let's begin where the first sheet of ice met open water. Maps flatten them into tidy blue shapes, contained and bordered, as if they were simple features of a continent. Yet scale reveals something far less modest. Laid across Europe, the combined surface of the Great Lakes would stretch from mountain ranges to distant capitals, rivaling bodies of water that carry the formal title of sea. Their shorelines sweep outward in long arcs, vanishing into haze, curving with the earth itself. When plotted beside enclosed seas such as the Baltic or the Black Sea, the comparison feels less poetic and more geometric. The measurements align, the expanse holds. Lake Superior, the largest among them, occupies an area greater than many European nations. Its basin plunges more than 1,300 feet at its deepest points, descending into cold, pressurized darkness where light cannot linger. That depth grants it mass, and mass grants it momentum. Water stacked so profoundly does not merely rest within a hollow of stone, it behaves, circulating in slow rotations that respond to wind stress and the Coriolis effect, forming gyres subtle yet persistent. In winter gales, waves can rise to more than 25 feet, their crests folding like those on a coastal horizon. The physics mirrors the open ocean, governed by fetch, wind velocity, and duration. With hundreds of miles of uninterrupted reach, energy builds without obstruction. Early European explorers, accustomed to Atlantic swells and salt spray, sailed into these waters and recorded seasickness. They noted tides of atmosphere rather than moon, storms that formed quickly and traveled with frightening coherence. Charts marked them as inland seas because language strained to describe anything smaller. Harbors required breakwalls. Lighthouses rose along rocky promontories. Ships were built with reinforced hulls to survive sudden squalls. Commerce moved across them as it would across marine passages, carrying grain, iron ore, and timber between distant ports, as though crossing a bordered gulf. Their breadth reshapes the air above them. In autumn, residual warmth rises into cooling skies, generating cloud bands that drift far beyond the shoreline. Pressure systems bending across North America adjust to this vast freshwater reservoir, redirecting fronts and moderating seasonal swings. Cyclonic systems traveling eastward gather moisture from their surfaces, altering precipitation patterns across provinces and states hundreds of miles away. Even in calmer months, breezes shift daily between land and water, establishing circulations reminiscent of coastal climates. To call them lakes remains technically correct, yet the term feels incomplete. By surface area, by depth, by wave energy, and by atmospheric influence, they function as enclosed seas, held gently within a continent. Their boundaries are terrestrial, but their behavior belongs to a grander category, shaped by scale alone. Long before ice ever forms, energy must be persuaded to leave. Water does not yield its warmth quickly. It absorbs summer sunlight molecule by molecule, storing that energy within the ceaseless motion of hydrogen bonds. Its specific heat capacity is unusually high compared to rock or soil, meaning that each degree of cooling requires an immense surrender of stored heat. Through autumn, while air temperatures swing sharply between warm afternoons and cold nights, the surface remains moderated by this invisible reservoir. The lake exhales slowly, resisting sudden change. That resistance has a name in physics: thermal inertia. It describes the reluctance of large bodies to alter their temperature in response to shifting conditions. A shallow pond may skim with ice after a brief frost because its limited volume holds little energy to release. A vast basin responds differently. The greater the volume, the deeper the archive of warmth beneath the surface. Even as cold air presses downward, convection begins its quiet work. Surface water cools, grows denser as it approaches 4 degrees Celsius, and sinks. Slightly warmer water rises to replace it. Wind drags across the surface, transferring momentum into the upper layers, stirring them into motion. This wind-driven mixing prevents the cold from settling in one place for long. Throughout summer, sunlight penetrates the upper layers and builds a thermal gradient, warm above and cool below. As autumn advances, that stratification collapses in a process known as turnover. The entire column approaches a more uniform temperature, redistributing heat that had been stored near the surface months before. By early winter, much of the water may hover just above freezing, yet the deeper regions still contain energy enough to delay solidification. Depth becomes a shield. Pressure increases with each descending meter, and the vast lower layers exchange heat only gradually with the air above. Oceans demonstrate this principle on a planetary scale. Despite frigid polar winds, most of the open sea remains liquid because its depth and circulation continuously transport warmth. Currents carry tropical heat toward higher latitudes, while mixing events prevent thin skins of ice from thickening easily. Only in enclosed or shallow margins does freezing advance extensively. Within the Great Lakes, the same laws apply. Wind stress, density shifts, and stored summer heat collaborate in a quiet defense against winter. Ice begins only after repeated nights of sustained cold, when the balance finally tips and the uppermost layer loses energy faster than deeper water can replace it. Until that threshold is crossed, the surface may darken and cool, yet beneath it the memory of sunlight endures, slowing the advance of frost across an inland sea. Freezing begins not with stillness, but with a subtle rearrangement hidden within the water itself. As temperature falls toward 4 degrees Celsius, liquid water reaches its greatest density. Molecules draw closer, tightening their formation, and the cooling surface sinks in slow, graceful currents. Yet when the temperature slips below that threshold, the pattern reverses. Water becomes lighter as it approaches its freezing point, rising instead of descending. This small anomaly governs the entire architecture of winter. Because of this shift, lakes solidify from the top down. Once the uppermost layer cools to the freezing point, it remains at the surface rather than sinking. There, it lingers, exposed to cold air and radiating heat into the night sky. Energy continues to leave molecule by molecule until the first microscopic crystals appear. Nucleation begins around tiny imperfections, bits of dust, suspended particles, or faint disturbances within the liquid. A lattice forms, delicate and geometric, expanding outward in branching patterns too fine for the eye to follow. When enough crystals connect, a thin skim of ice spreads across the surface like a breath becoming visible. Atmosphere plays its part with careful precision. Calm conditions allow the surface to cool evenly, undisturbed by turbulence. In still air, a fragile skin can stretch surprisingly far overnight, translucent and glass-like. Wind, however, delays this quiet construction. Gusts shear apart, forming crystals, mixing slightly warmer water upward and importing marginal heat from below. Waves fracture young ice, piling shards together along leeward shores where they freeze into irregular margins. The contrast between calm and wind does not change the physics of freezing, but it alters the rhythm and pattern through which ice establishes itself. Once a continuous sheet forms, another transformation begins. Ice acts as an insulator, reducing direct exchange between water and air. Heat now escapes more slowly, yet it continues to do so. The underside of the ice thickens downward as additional layers freeze in contact with water just at the freezing point. Growth proceeds gradually, its rate governed by air temperature, snow cover, and the conductivity of the ice itself. Snow can blanket the surface, reflecting sunlight and limiting further thickening, or it can compress into slush that later refreezes, adding uneven strength. Beneath this developing lid, water remains liquid, held near 4 degrees Celsius by the same density anomaly that initiated freezing. Life persists in that narrow thermal refuge, and gentle currents continue their subdued circulation. The lake does not become a solid block, it becomes layered, structured by temperature and phase. What appears from above as a single frozen plain is in truth a dynamic boundary, a conversation between air and water written in crystalline form, high above the clouds, far beyond the reach of lake spray and shoreline wind. A ring of cold air circles the pole in near darkness. It forms each winter as sunlight fades from the Arctic, allowing the upper atmosphere to cool and contract. This tightening of temperature gradients strengthens a broad whirl of westerly winds known as the polar vortex. When stable, it remains contained, spinning quietly over the high latitudes like a lid holding winter in place. Yet the atmosphere is rarely still. In certain years, waves of energy rise upward from the lower layers of air, disturbing the stratosphere. These planetary waves, shaped by mountain ranges and uneven heating, can disrupt the vortex in what scientists call a sudden stratospheric warming event. Temperatures high above the surface may climb rapidly, not as a sign of comfort, but as a signal of imbalance. The once circular vortex weakens, stretches, or even splits. Cold air that had been confined begins to wander. At the same time, the jet stream below responds. This fast-moving river of air, normally flowing in a relatively smooth path from west to east, develops deep undulations. Ridges arch northward, while troughs plunge southward. Within those troughs, Arctic air descends into mid-latitudes, carrying with it temperatures far below seasonal averages. What had been distant polar cold now settles across cities and shorelines, unaccustomed to such persistence. During extreme winters, surface observations record anomalies of staggering scale. Thermometers drop well below long term means, sometimes by tens of degrees. Night after night, readings remain suppressed, offering little daytime recovery. Wind amplifies the effect. Wind chill, a measure of how quickly heat is drawn from exposed skin, may suggest conditions far harsher than the actual air temperature. Though wind chill does not alter the freezing point of water itself, it accelerates the loss of energy from any surface it touches, including open water exposed to relentless gusts. When such an outbreak anchors over the Great Lakes, the cumulative effect becomes profound. Air masses arriving from the Arctic are dry and dense, promoting clear skies that enhance radiative cooling at night. Strong pressure gradients sustain persistent winds, increasing sensible and latent heat flux from the surface. The balance tips steadily, not through a single dramatic plunge, but through sustained withdrawal of warmth. The altered vortex, the dipping jet stream, and the prolonged presence of Arctic air align in rare synchrony. In those seasons, the atmosphere no longer shields the inland seas from winter. Instead, it channels cold directly toward them, maintaining it with unusual tenacity. What begins as a distant disturbance high above the pole translates, step by step, into bitter air sweeping across open water, reshaping the destiny of an entire freshwater system. In the early days of that winter, the transformation announced itself quietly, first in data, then in color. Analysts studying orbital imagery noticed pale formations spreading outward from sheltered bays, tracing coastlines with widening bands of white. What had once been open, steel gray water began fragmenting into flows, then merging into fields. Within weeks, the expansion accelerated beyond routine seasonal growth. By late winter, ice coverage approached roughly 90% across all 5 lakes, a level not witnessed in many years. The season of 2013 to 2014 unfolded under the persistent influence of Arctic air, which lingered and returned in repeated waves. Each surge reinforced the last, sustaining below average temperatures across the basin. Surface cooling intensified, and once a continuous sheet established itself in one region, it provided a stable platform for further growth. Protected embayments froze first, followed by broader expanses exposed to steady cold. Satellite composites revealed a mosaic, gradually simplifying into near uniform white. As ice thickened, navigation corridors narrowed. Commercial vessels that typically threaded through designated routes found passages increasingly constrained by pressure ridges and compacted fields. Icebreakers labored to maintain channels, their reinforced bows riding up and crushing through layered slabs. Even so, several shipping lanes closed earlier than expected. Ports adjusted schedules, and some cargo shipments were delayed until spring. Iron ore destined for steel production, grain bound for export, and coal shipments faced logistical bottlenecks. The economic ripple extended beyond shorelines, influencing supply chains across the region. Shore-based communities witnessed subtle shifts. Ferry services suspended operations. Recreational marinas remained locked in stillness. Energy demand rose as prolonged cold required additional heating across cities bordering the lakes. At the same time, the expansive ice cover altered heat exchange between water and atmosphere, contributing to modifications in local weather patterns as winter matured. Orbital observations provided a detached yet compelling perspective. Comparing imagery from earlier winters to that singular season revealed stark contrast. In many recent years, large stretches of dark water persisted well into late winter. During 2013 to 2014, the lakes appeared almost contiguous with the surrounding snow-covered land, boundaries softened by frost. Analysts overlaid temporal sequences, watching the progression day by day as open water receded and consolidated ice advanced. Though not every harbor sealed completely, and some central basins retained pockets of movement, the collective coverage approached a rare threshold. The inland seas, so resistant in typical winters, displayed the scale of what sustained atmospheric alignment could accomplish. The record stands not as anomaly alone, but as demonstration, illustrating how swiftly a vast freshwater system can shift when cold remains steadfast and unbroken. Long before satellites rendered the lakes in daily mosaics, winter left its signature in harbor records and shoreline journals. The season of 1978 to 1979 unfolded with a steadiness that felt almost immovable. Cold did not merely visit, it remained. Snow accumulated early, and temperature departures from seasonal norms persisted for weeks at a time. By midwinter, ice coverage expanded across the basin toward near record levels, rivaling the most extensive freezes documented in modern measurements. The atmospheric pattern driving that season differed in texture, yet achieved similar consequence. Repeated cold waves descended in succession, each reinforcing the chill left by the one before. High-pressure systems settled broadly across central North America, maintaining clear skies that encouraged radiational cooling during long nights. Without meaningful thaw intervals, surface temperatures remained suppressed, allowing ice to thicken gradually and continuously. Wind direction shifted at key moments, compressing drifting flows toward particular shorelines and encouraging consolidation across open reaches. Communities bordering the lakes adapted as they had for generations. Fishing vessels were pulled from slips earlier than usual. Ferries suspended crossings, and coastal infrastructure endured mounting pressure from expanding ice sheets driven shoreward by persistent winds. In certain harbors, pressure ridges accumulated into jagged barriers, altering familiar winter landscapes. Shorelines that typically retained pockets of open water lay sealed for extended periods. Travel routes adjusted accordingly, and economic rhythms slowed in response to limited navigation. Compared with later freeze events observed through satellite archives, the winter of 1978 to 1979 appears both similar and distinct. In modern seasons, rapid expansions can be traced day by day from orbit, revealing swift transitions under extreme atmospheric alignment. During that earlier freeze, growth proceeded with relentless consistency rather than sudden acceleration. The result, however, converged toward comparable coverage, demonstrating that sustained cold can match even the most dramatic outbreaks in cumulative effect. Instrumental data collected at coastal stations recorded prolonged intervals of below average air temperature with only modest mid-season moderation. Ice thickness reports from maritime authorities indicated substantial buildup in sheltered bays and along central corridors, sufficient to challenge available ice-breaking capacity at the time. Yet beneath the severity lay a familiar orchestration of physics and atmosphere, the same principles that govern every freeze, simply extended over a longer duration. When placed beside contemporary winters, the historic season stands as reminder that variability has always shaped the lakes. Some years yield modest ice fringes, others approach comprehensive coverage. The freeze of 1978 to 1979 belongs to the upper range of that natural spectrum, illustrating how wind patterns, pressure placement, and persistent cold can align to quiet even the largest freshwater expanses along the continent's heartland. Speed, in winter, is rarely a single moment. It is an accumulation measured in degrees lost, in joules surrendered, in the quiet arithmetic of surface area exposed to relentless air. An inland sea does not leap from motion to silence in an instant. It advances through stages, each governed by temperature, wind, and the exchange of energy between water and sky. Yet, under extreme cold, that progression can compress into a span that feels startlingly brief. When air temperatures plunge far below seasonal norms and remain there without relief, the rate of ice growth accelerates. Heat flux from the surface intensifies, driven by sharp contrasts between water hovering near the freezing point and air descending from Arctic latitudes. In such conditions, newly formed ice can thicken by several centimeters in a single day. Thin sheets expand laterally across calm expanses, welding together as fraisal crystals accumulate and consolidate. Each hour of sustained cold compounds the effect, reducing open water incrementally but persistently. Scale amplifies perception. The Great Lakes encompass tens of thousands of square miles, an area so vast that minor percentage changes translate into immense swaths of altered surface. If even a small fraction of that expanse transitions from liquid to solid within a short interval, satellite imagery registers dramatic visual contrast. Dark blues and grays give way to pale textures that spread across the basin like frost across glass. Analysts comparing sequential images have observed coverage increasing by noticeable margins over just a few days during extreme outbreaks. Calm nights play a decisive role in these surges. Without wind to stir upper layers or fracture delicate films, the surface cools evenly and radiates heat efficiently into clear skies. Under such radiational conditions, temperature gradients between water and atmosphere steepen, encouraging rapid formation of continuous sheets. What forms quietly under darkness may greet morning light as a newly unified expanse, altering the lake's appearance in a single dawn. The phrase overnight, often spoken in headlines, captures this visual transformation more than the physical process itself. The physics unfold over days of cumulative cooling, yet perception hinges on contrast. When observers look across water one evening and return the next to find broad stretches sealed, the shift feels abrupt. Remote sensing reinforces that impression, compressing temporal sequences into vivid, side by side comparisons that reveal swift transitions during peak freeze periods. Measured precisely, freezing remains bound by thermodynamics and constrained by stored heat. Felt experientially, it can seem sudden when atmospheric alignment persists long enough for thresholds to be crossed in quick succession. In those rare intervals, an inland sea appears to change almost at once, though the quiet preparation has been underway for far longer than a single night. Motion defines a lake long before ice defines its absence. Wind passing over open water transfers energy through friction, setting molecules into motion that gather into ripples, then into organized waves. With sufficient fetch, those waves lengthen and steepen, transporting momentum across miles of surface. Beneath them, orbital water movement circulates in widening loops, while surface currents align with prevailing winds. Even in cold seasons, this continuous exchange between air and water sustains a restless rhythm. As freezing advances, that rhythm begins to soften. The first thin sheets, forming along sheltered margins, act like breaks, absorbing and scattering incoming wave energy. Instead of traveling uninterrupted, swells encounter flexible plates that bend and dampen their force. Collisions between fragments fracture energy into smaller oscillations, each one weaker than before. Open corridors narrow, reducing the distance over which wind can build significant waves. The physics shift from amplification to suppression. When a broad, continuous sheet establishes itself, the transformation becomes profound. Ice decouples wind from liquid, removing the primary mechanism of momentum transfer. Surface currents diminish as frictional forcing fades. The orbital motion beneath waves collapses because the waves themselves cease to propagate. Water below the ice remains mobile in subtle ways, responding to density gradients and slow basin-wide circulations, yet the surface appears fixed. What had been dynamic becomes restrained by a crystalline lid. Acoustics change alongside motion. Open water produces a constant tapestry of sound, from low-frequency wave impacts to the hiss of spray driven by gusts. These vibrations travel through air and water alike, forming an ever-present background along the shoreline. When ice spreads, many of those sounds vanish. Wind passing over a frozen surface carries a muted tone, less textured than wind interacting with waves. At times, ice introduces its own voice, distant cracks and resonant booms caused by thermal contraction and stress redistribution. These sounds travel efficiently through solid sheets, carrying across miles with unexpected clarity, yet they remain intermittent, separated by long intervals of near silence. For communities accustomed to winter gales rolling in from open water, the stillness alters perception. Harbors that once echoed with wave impact settle into a subdued calm. The horizon, no longer animated by shifting crests, holds a uniform stillness that reshapes the visual field. Light reflects differently from frozen expanses, appearing flatter, less fragmented. The inland sea retains its scale, yet its character shifts from kinetic to composed. Beneath that composed exterior, energy has not vanished, it has changed state. The pathway through which wind once communicated with water now terminates at ice. In that quiet interruption, waves relinquish their motion, and the vast surface settles into a different form of presence, steady and restrained under winter's influence. Long before the surface turned white in any single season, quiet records had already begun to accumulate. Along shore stations and research vessels, measurements were logged year after year, noting the reach of winter across the lakes. In the modern era, agencies such as the National Oceanic and Atmospheric Administration consolidated those observations into systematic ice tracking programs, combining aerial surveys with satellite analysis to map coverage with growing precision. What emerged over decades was not a simple pattern of steady increase or decline, but a rhythm shaped by variability. Through the 1960s and 1970s, several winters produced extensive ice coverage, with multiple seasons approaching high percentages across the basin. Cold air outbreaks were frequent, and atmospheric configurations favored sustained freezing. These years stand prominently within the historical archive, often cited when comparing later events. Yet even within that colder era, not every winter behaved alike. Some seasons brought widespread consolidation, while others relaxed into more moderate expressions of ice. Decadal trends reveal oscillation rather than uniformity. Large-scale climate patterns, including fluctuations in ocean temperatures and atmospheric pressure gradients, exert subtle influence over North American winters. When certain oscillations align to favor meridional jet stream flow and amplified troughs over central Canada, the lakes experience prolonged cold. In other phases, westerly flow dominates, drawing milder Pacific air eastward and limiting ice growth despite the calendar's advance into midwinter. These shifting alignments do not follow a strict schedule. They ebb and return across years in complex interplay. By the late 20th century and into the early 21st, a general tendency toward reduced average ice cover became apparent in many analyses. Warmer baseline temperatures shortened the duration of freezing in some years, and complete basin-wide consolidation grew less common. Yet variability persisted. Even within a warming context, certain winters surged toward high coverage when atmospheric patterns temporarily favored Arctic incursions. The record, therefore, reads as layered rather than linear, with extremes punctuating broader trends. Some winters remain mostly open water because thresholds are not crossed. Air temperatures may fluctuate around the freezing point without sustaining the prolonged deficits required for widespread ice formation. Wind conditions may prevent stable sheets from establishing, or early thaws may interrupt gradual thickening. In those seasons, the lakes retain broad expanses of dark surface well into late winter, absorbing sunlight and moderating nearby climates. The historical archive, maintained through patient observation and advancing technology, offers perspective without alarm. It shows that the inland seas have long responded to the shifting architecture of atmosphere and climate, sometimes closing tightly under persistent cold, at other times remaining largely fluid. Within that archive lies the quiet memory of winters past, each one inscribed in maps of ice that mark the changing balance between air and water. Snow sometimes begins far from any mountain, born instead from the quiet exchange between cold air and comparatively warmer water. When frigid air flows across open expanses of the Great Lakes, it absorbs moisture through evaporation and sensible heat flux. The temperature contrast destabilizes the lower atmosphere, encouraging rising motion. As that moisture-laden air ascends and cools, clouds form in elongated bands aligned with prevailing winds. These lake effect systems can intensify rapidly, releasing concentrated snowfall downwind, while regions only a few miles away remain comparatively clear. The process depends upon exposure. Open water provides both vapor and heat, acting as a localized engine within winter's broader pattern. Even when air temperatures linger well below freezing, evaporation continues so long as the water surface remains unfrozen. Invisible molecules lift from the lake and enter the passing air mass, increasing its humidity. Convection strengthens, cloud tops rise, and precipitation efficiency improves. Shore communities often recognize the pattern, watching skies darken as bands organize and drift inland. When ice spreads widely across the surface, that engine weakens. A continuous sheet limits direct contact between liquid water and air, sharply reducing evaporation rates. Without that sustained moisture supply, the lower atmosphere loses its buoyant instability. Cloud bands thin, shorten, or fail to develop altogether. Snowfall totals decline in regions that normally receive heavy accumulations from lake effect processes. The change can feel abrupt in seasons when extensive freezing follows a period of open water storms. Regional weather responds in measured ways. With diminished lake effect activity, temperature contrasts near the shoreline soften, and localized pressure gradients adjust. Reduced snowfall alters surface albedo, influencing how much solar radiation is reflected back into the atmosphere. In some years, early ice formation contributes to clearer intervals between broader synoptic systems, subtly reshaping winter's cadence. Communities accustomed to frequent squalls notice longer stretches of still air and brighter skies once the lakes are largely sealed. This transition does not eliminate snowfall altogether. Large-scale storm systems continue to traverse the continent, delivering precipitation independent of lake influence. Yet the distinctive bursts associated with open water become less pronounced. The inland seas, once amplifying winter through moisture and heat exchange, shift toward a more passive role beneath their frozen cover. Thus, the same surface that earlier fueled narrow corridors of intense snow can later quiet them simply by changing phase. Open water breathes into the cold, feeding clouds with vapor drawn upward by stark temperature differences. Ice interrupts that conversation, muting the exchange and altering patterns across hundreds of miles. In this way, the presence or absence of a frozen lid shapes not only the lakes themselves, but also the character of winter weather far beyond their shores. Freighters usually move across the lakes with a steady, deliberate grace, their hulls carrying iron ore, grain, coal, limestone, and finished steel between distant ports. Over the course of a typical navigation season, hundreds of millions of tons of cargo pass through this freshwater corridor, feeding blast furnaces, food processing plants, and construction projects far beyond the shoreline. The system operates like an inland artery, linking mines in the north to mills in the south and farms in the west to export terminals near the Atlantic. When heavy ice establishes itself across key channels, that artery narrows. Icebreakers deploy first, their reinforced bows riding up onto frozen surfaces before crushing downward with measured force. Their engines strain against thickening plates, carving navigable paths through compacted flows, yet their capacity has limits. As pressure ridges accumulate and fields consolidate under persistent cold, even these specialized vessels slow. Channels must be reopened repeatedly after drifting ice compresses them closed again, and each transit demands coordination between captains, pilots, and coast authorities. Some ports close entirely when approaches become impassable. Harbors that normally echo with loading cranes and conveyor belts fall quiet, their piers locked against shore by immobile ice. Ore carriers, scheduled to deliver raw material to steel plants, remain at anchor or delay departure until conditions ease. Grain shipments destined for overseas markets pause mid-route, awaiting clear passage. Inventories at receiving facilities tighten, forcing adjustments in production schedules. The ripple moves outward in subtle increments. Rail networks compensate where possible, absorbing part of the cargo that cannot travel by water, yet capacity differs and costs shift accordingly. Energy demand rises in industrial centers already contending with extreme cold, placing additional strain on supply chains. Insurance calculations account for delayed voyages and elevated operational risks. Each frozen corridor carries implications beyond its visible boundary. Navigation calendars, carefully planned around average ice-out dates, become less predictable in years of extensive coverage. Shipping companies monitor forecasts and ice charts closely, balancing economic urgency against safety considerations. Crews operate under stricter constraints, navigating narrow leads between consolidated fields with vigilance. Despite these disruptions, the system demonstrates resilience. Once thaw returns and channels reopen, traffic resumes with renewed intensity, clearing backlogs and restoring flow. Yet the interlude of shutdown reveals the degree to which industry depends on liquid water. The lakes are not only scenic horizons, they are logistical frameworks supporting vast economic networks. Under expansive ice, that framework pauses, Steel production slows for want of ore, export schedules adjust for lack of grain movement, and harbor towns adapt to weeks of stillness. The frozen surface, serene from a distance, conceals a temporary suspension of commerce beneath its quiet expanse. Steel meets winter with deliberate intention. Long before most vessels retreat from advancing ice, specialized ships prepare to move directly into it. Icebreakers are built not for speed or elegance, but for controlled force. Their purpose is simple in principle, yet demanding in execution: to fracture a frozen surface so that others may pass. Unlike conventional hulls that slice cleanly through open water, an icebreaker's bow is rounded and reinforced. Rather than cutting horizontally into ice, it rides upward onto the surface. The weight of the vessel then presses downward, using gravity to crack the sheet beneath it. Thick plating and closely spaced frames distribute stress along the hull, allowing it to withstand repeated impacts. Beneath the waterline, the structure is strengthened to resist abrasion from submerged fragments grinding along steel. Propulsion systems are equally robust. Powerful engines drive multiple propellers, often designed to clear ice pieces away from the stern. Some vessels employ air bubbling systems along their sides, releasing streams that reduce friction between hull and ice. By loosening contact, they can maneuver more effectively within dense fields. Each advance is incremental. The ship surges forward, climbs slightly onto the frozen plate, fractures it, then continues through the broken channel it has created. Yet ice rarely forms as a uniform plane. Wind and current push floating sheets together, compressing them into pressure ridges that rise above the surface and extend far below. These ridges consist of stacked slabs, sometimes several meters thick, interlocked in chaotic arrangement. Beneath them, keels of compacted ice can reach depths capable of striking even reinforced hulls. Navigating through such features demands precision and caution as resistance increases dramatically. In extreme seasons, repeated cycles of freezing and compression produce consolidated expanses that challenge even the strongest vessels. When thickness grows beyond design tolerance, or when ridges accumulate faster than they can be cleared, channels narrow or close altogether. Icebreakers may open a path only to see it refreeze or compress within hours under sustained wind. Progress slows, fuel consumption rises, and escort schedules adjust accordingly. Despite these obstacles, icebreakers embody a remarkable adaptation to winter's force. They do not eliminate ice, they reshape it, temporarily redistributing mass to maintain movement where possible. Their presence transforms static barriers into managed corridors, allowing commerce and essential transit to persist through conditions that would otherwise halt all passage. Still, there are moments when the frozen surface asserts dominance. Under prolonged cold and continuous compression, some regions become effectively impassable until thaw returns. In those intervals, even the most formidable hull meets its limit, and the inland sea remains sealed by the accumulated strength of its own winter architecture. Below the hardened surface, the lake does not sleep. Light fades as snow and ice thicken above, filtering the sun into a dim blue haze that reaches only a fraction of its former depth. The world beneath grows quieter, yet it remains alive with subtle movement and exchange. Water just below the ice hovers near the freezing point, while deeper layers retain slightly warmer temperatures, creating a stable refuge for organisms adapted to winter's restraint. Fish alter their behavior with the season's advance. Many species reduce activity, conserving energy as metabolic rates slow in cold water. Rather than roaming broadly, they gather along gentle gradients where temperature and oxygen remain steady. Some descend toward deeper basins, where conditions change more gradually. Others linger near submerged structures that offer shelter from faint under ice currents. Movement becomes economical, deliberate, shaped by the need to endure rather than expand. Oxygen, though less visibly dramatic than ice, governs much of this underwater life. During open water months, wind and wave action mix the upper layers, replenishing dissolved oxygen from the atmosphere. When ice seals the surface, direct exchange diminishes. The lake must rely on oxygen already dissolved and on internal processes to sustain its inhabitants. In clearer systems with lower biological demand, levels remain sufficient through winter. In shallower or nutrient rich regions, consumption by microbes and respiring organisms can outpace replenishment, gradually lowering concentrations. Most of the Great Lakes, owing to their size and mixing patterns before freeze, maintain adequate oxygen reserves, though localized depletion may occur in sheltered embayments. Reduced light penetration shapes the base of the food web. Snow cover reflects much incoming radiation, and ice scatters what remains. Phytoplankton, microscopic photosynthetic organisms, persist in diminished abundance beneath the frozen lid. Some species adjust by slowing growth and entering dormant phases, relying on stored energy or adapting to lower light thresholds. Others exploit brief, clear intervals when wind removes snow or when midwinter sun angles allow slightly greater transmission. Their survival ensures continuity for zooplankton and, in turn, for fish that depend on them. Winter food chains operate at a subdued tempo. Predatory fish continue to feed, though less aggressively than in warmer months. Invertebrates graze upon sparse phytoplankton or detrital material settling through the column. Energy transfer does not halt, it contracts, guided by the constraints of temperature and light. The lake becomes a layered system, balanced between scarcity and endurance. Above, the surface may appear locked and silent. Beneath, respiration, slow circulation, and fragile productivity persist. Life adjusts to the altered boundary, drawing upon reserves accumulated during brighter seasons. Under ice, the inland sea remains inhabited, its ecological networks narrowed but unbroken, awaiting the gradual return of light and open water. In the height of summer, the lake arranges itself into quiet layers. Sunlight warms the upper waters, creating a buoyant surface zone that rests lightly above cooler depths. This warm layer, known as the epilimnion, absorbs wind energy and interacts freely with the atmosphere. Beneath it lies the thermocline, a boundary where temperature drops rapidly with depth, forming a transitional gradient. Below that, the hypolimnion remains cold and comparatively undisturbed, holding a reservoir of dense water insulated from the heat above. This stratified structure is stable for months. Density differences act like invisible scaffolding, preventing vertical mixing. Nutrients, oxygen, and heat remain unevenly distributed, each confined largely to its respective layer. Surface waters circulate under summer breezes while deeper regions move slowly, guided more by basin-scale currents than by wind. The arrangement persists until seasonal cooling begins to erode the contrast. As autumn advances, cooler air lowers the temperature of the surface layer. Gradually, it approaches the temperature of the water below. When the difference diminishes sufficiently, density no longer resists vertical exchange. Wind passing across the surface can then stir the entire column, blending epilimnion and hypolimnion into a more uniform state. This event, known as fall turnover, unfolds not in a single day, but through sustained cooling and steady agitation. The significance of this mixing extends into winter. By redistributing stored summer heat downward and upward alike, turnover ensures that the lake begins the freezing season with a relatively consistent temperature profile. Oxygen from the surface descends to deeper waters, supporting aquatic life through the months ahead. Nutrients rise from the depths, setting the stage for productivity when light returns in spring. Without turnover, isolated layers could retain stark contrasts, altering the dynamics of freeze and survival beneath the ice. Most importantly, for winter's progression, mixing exposes the entire water column to the gradual loss of heat. Instead of maintaining a deep reservoir of comparatively warmer water sealed beneath a cool surface, the basin approaches a balanced state. Once uniform temperatures near 4 degrees Celsius are achieved, the density anomaly of water prepares the system for surface freezing. The sequence is orderly, shaped by thermodynamics rather than chance. In large lakes, turnover may take weeks to complete, especially in the deepest basins. Wind energy must be sufficient to overcome any lingering gradients, and cooling must persist long enough to eliminate residual stratification. When the process concludes, the inland sea stands poised at a threshold. Summer's layering has dissolved, replaced by a fully integrated column prepared for winter's next transformation, its heat evenly distributed and gradually surrendering to the advancing cold. Freezing is not merely a drop in temperature, but a change of state that demands a final, invisible payment. Even after water cools to its freezing point, it must surrender additional energy before solid ice can form. This hidden cost is known as the latent heat of fusion, the energy required to reorganize liquid molecules into a crystalline lattice without lowering temperature further. It is an immense exchange occurring silently at the boundary between fluid and solid. For a small volume of water, the demand is modest. For an inland sea, it becomes staggering. Each kilogram must release the same amount of latent heat, and when multiplied across billions upon billions of kilograms, the total climbs to levels difficult to grasp. Before a single widespread sheet can thicken, the lake must shed not only the warmth accumulated through summer and autumn, but also the stored molecular energy bound within its liquid state. The atmosphere, through sustained cold and persistent wind, acts as the withdrawing force, drawing that energy upward in steady increments. Scientists estimate total seasonal energy loss in terms of heat flux across the surface. Calculations account for sensible heat, latent heat transfer through evaporation, and long-wave radiation emitted toward clear winter skies. When aggregated across tens of thousands of square miles, the cumulative loss equals many trillions of joules. To place this in perspective, the energy required to freeze even a fraction of the Great Lakes rivals the output of large power stations operating continuously for extended periods. The comparison underscores scale rather than spectacle. It reveals how much thermal inertia must be overcome before ice can claim dominance. Power generation plants convert chemical or nuclear energy into electricity measured in gigawatts. The freezing of a vast freshwater basin involves comparable magnitudes, though dispersed across open sky rather than concentrated within turbines. Instead of wires carrying current outward, the atmosphere carries energy upward and away, redistributed through global circulation. The process is gradual, governed by thermodynamic constraints that cannot be rushed beyond physical law. What makes freezing such a body extraordinary is not simply its visible extent, but the endurance required of winter to accomplish it. Cold must persist long enough to remove accumulated heat, then persist further to extract the latent reserve. Any interruption, any prolonged thaw or shift in wind pattern can stall progress and return the system toward liquidity. Only under sustained alignment does the balance tip decisively. Thus, when broad expanses of the lakes solidify, the achievement belongs to physics patiently applied. The surface may appear calm and pale, yet beneath that stillness lies the record of immense energy exchanged between water and sky, a transformation measured not in moments, but in vast quantities, quietly surrendered to the cold. Thickness reveals itself gradually, not in a single glance, but through weeks of accumulation. After a continuous sheet forms and air temperatures remain suppressed, the ice begins to grow downward into the water below. In many winters, typical thickness across broad expanses measures several inches to more than a foot, sufficient to support snow cover and to reshape the character of the surface. In harsher seasons, prolonged cold allows growth to extend far deeper, particularly in sheltered bays where motion has long been subdued. The strength of ice depends not only on thickness but also on structure. Clear, black ice formed under calm conditions tends to be dense and comparatively strong, its crystalline lattice aligned with minimal trapped air. White ice, created when snow saturates and refreezes atop the sheet, contains more pockets and irregularities, reducing overall integrity. Layers may alternate as weather fluctuates, producing a stratified slab with variable resistance to stress. Wind transforms flat expanses into textured architecture. As sustained gusts push against the surface, large plates drift slowly until they encounter barriers, either opposing flows or the shoreline itself. The collision forces pieces upward and downward, stacking them into pressure ridges. Above the surface, ridges may rise several feet in jagged formations. Beneath, keels extend downward into the water, forming submerged walls of compacted ice. These structures redistribute mass, concentrating thickness along narrow lines while leaving adjacent areas relatively thinner. Repeated cycles of compression intensify this stacking. When wind direction shifts, ridges may fracture and reform elsewhere, altering internal stresses within the sheet. Over time, fields that began uniform evolve into patchwork terrains shaped by external forcing. The apparent simplicity of a frozen lake conceals a dynamic balance between cohesion and fracture. Along shorelines, wind and expanding ice sometimes produce a phenomenon known as ice shove. As temperatures fluctuate, thermal expansion adds incremental pressure to already compressed fields. When persistent wind aligns with that expansion, entire sections may advance toward land, sliding across shallows and pushing against beaches, docks, and protective structures. The force can be considerable, sufficient to displace rocks or damage built features. Yet the event unfolds as a gradual heave rather than a sudden surge, the slow transfer of momentum across thousands of tons of frozen mass. Despite its rigidity, ice remains responsive to stress. It bends slightly under weight, creaks as temperatures drop, and fractures when limits are exceeded. Its structural strength is therefore a product of thickness, composition, and external force acting in concert. On a calm winter day, the surface may appear solid and immutable. Beneath that appearance lies a shifting architecture, strengthened by cold, sculpted by wind, and bound by the same physical laws that shaped its formation. Along exposed shorelines, winter sometimes builds in silence and then reveals itself in sculpture. Stone piers, steel railings, and tall lighthouses that guide ships through warmer months become canvases for a different kind of construction. When wind drives water against these structures during sub-freezing conditions, each impact throws a fine mist into the air. That mist freezes almost instantly upon contact, layer settling upon layer, slowly encasing solid forms in thick shells of ice. This process, known as spray icing, depends on repetition. Waves strike, droplets rise, and freezing air extracts heat in moments. A railing gathers a thin coat, then another, until delicate shapes transform into heavy columns. Stairways lose their sharp edges beneath rounded contours. Lighthouse towers, built to endure storms, grow luminous and opaque, their lantern rooms entombed in translucent armor. What begins as a protective structure becomes part of the frozen landscape itself, reshaped not by human design, but by accumulated impact. Wind determines orientation and texture. On the windward side, ice grows thicker and more chaotic, sculpted into ridges and fluted patterns by persistent gusts. On the leeward side, growth may remain smoother, shielded from direct spray. Icicles extend from overhangs and railings, elongating as meltwater from brief daytime sun refreezes overnight. The entire composition responds to shifts in temperature and direction, evolving with each passing front. Farther along natural beaches, another phenomenon emerges. When waves break through holes in nearshore ice and force water upward, that water can freeze around the opening, gradually building conical mounds known as ice volcanoes. Slush and fragments accumulate around the vent, forming circular walls. With each surge, more water splashes upward, freezing upon contact and increasing the mound's height. Some volcanoes grow only modestly. Others reach several feet tall, punctuated by a small crater at the top where waves pulse below. These formations are not static. Under continued wind, cones may elongate or merge with neighboring mounds. If temperatures rise slightly, surfaces glaze and harden, creating glossy domes that shimmer in winter light. When cold intensifies again, fresh spray restores roughness, adding new layers to the structure. The shoreline becomes an evolving gallery of transient architecture, shaped by interplay between water in motion and air in deep freeze. Despite their intricate appearance, these sculptures arise from simple thermodynamics. Liquid water meets sub-freezing air, heat transfers rapidly, solid ice remains. Repeated thousands of times across hours and days, that sequence transforms human-built structures and sandy beaches alike. The frozen lighthouse and the ice volcano stand as visible records of winter's persistence, each contour mapped by wind, wave, and the steady surrender of warmth into the cold sky. Far beyond the horizon of any single shoreline, distant oceans and upper air currents begin shaping winter long before cold descends upon the lakes. The atmosphere is not confined to one region. It is a connected system, responding to subtle temperature differences that span entire hemispheres. In this wide orchestration, recurring climate oscillations influence how and where cold air gathers, and whether it remains contained or wanders southward. Across the tropical Pacific, cycles known as El Niño and La Niña alter global wind patterns through shifts in sea surface temperature. During El Niño phases, warmer waters in the eastern Pacific can strengthen the subtropical jet stream, often guiding milder air across portions of North America. La Niña, characterized by cooler eastern Pacific waters, tends to favor a more amplified flow, with increased likelihood of cold air intrusions into the continent's interior. These tendencies do not guarantee a specific outcome each year, yet they tilt probabilities, subtly adjusting the atmospheric stage upon which winter unfolds. Closer to the North Atlantic, another oscillation modulates pressure differences between subtropical highs and polar lows. The North Atlantic Oscillation influences storm tracks and the strength of westerly winds crossing the ocean. When in its positive phase, stronger west to east flow can confine Arctic air farther north. During a negative phase, weakened pressure gradients allow greater meridional motion, encouraging cold air to spill southward. Although centered over the Atlantic, its effects ripple inland, interacting with continental weather systems that reach the Great Lakes. Overlaying these patterns is the Arctic Oscillation, an index describing the distribution of pressure across the polar region. When the Arctic Oscillation remains positive, a robust ring of winds tends to contain frigid air near high latitudes. In a negative phase, pressure rises over the pole and weakens that ring, permitting lobes of cold air to extend into mid-latitudes. The distinction may appear technical, yet its practical impact can be profound. Extended negative phases often coincide with prolonged cold spells across parts of North America. These oscillations intertwine with one another and with shorter-term atmospheric waves, creating winters that are neither random nor fully predictable. Some seasons align in ways that favor frequent Arctic outbreaks and sustained below-average temperatures. Others balance differently, yielding milder intervals and limiting ice growth despite the calendar's progression. Over decades, variability emerges as a defining trait. Extremes cluster at times, then recede, reflecting the shifting interplay of ocean temperatures, atmospheric pressure, and energy distribution across the planet. In this broader context, an extreme winter on the lakes is not an isolated event. It is an expression of hemispheric dynamics unfolding through interconnected patterns. The ice that forms at the surface carries echoes of distant seas and high-altitude winds, woven together in a rhythm larger than any single basin. On certain winters, maps reveal nearly unbroken white, stretching from one shoreline to the next, and the question arises quietly in the background of such imagery. Can every lake seal completely at once? History offers partial answers. Lake Erie, the shallowest of the five, has frozen over entirely in multiple documented seasons. Its average depth is modest compared with its neighbors, allowing heat to dissipate more quickly under sustained cold. With limited volume to buffer temperature change, it responds rapidly when atmospheric conditions persist. Lake Superior presents a different challenge. Its immense depth and volume grant it formidable thermal inertia. Even after prolonged outbreaks of Arctic air, portions of its central basin often remain open or covered only by fractured fields rather than solid, continuous ice. The deeper a lake, the greater the store of energy that must be removed before freezing can extend across its entirety. In Superior's case, that reservoir is vast, making complete coverage rare, though not entirely beyond historical record. Bathymetry shapes destiny. Lakes Michigan and Huron, connected by the Straits of Mackinac, share intermediate depths and complex circulation patterns. They have approached very high coverage in extreme winters, yet small sectors may persist as open water when winds concentrate thinner ice elsewhere. Lake Ontario, influenced by relatively greater depth and by inflow from upstream basins, also tends to resist full consolidation. Each basin carries its own geometry, and geometry governs heat distribution and exposure. Modeling studies simulate combinations of prolonged negative Arctic oscillation phases, persistent clear skies, and limited mid-season thaw. Under sufficiently extended cold, projections indicate that near complete coverage across all five lakes remains physically plausible. The requirement, however, is duration as much as intensity. Air temperatures must remain well below seasonal norms for weeks without interruption, and wind patterns must not repeatedly fracture, forming sheets before they thicken sufficiently to stabilize. Even then, small polynyas or leads may appear intermittently, especially in deeper central areas where residual heat lingers. Complete freezing, in a strict sense, implies a continuous, stable sheet across every basin. That scenario stands near the upper boundary of observed variability. Historical archives suggest it has not occurred simultaneously across all five in modern record, though individual lakes have approached that condition in separate winters. Thus, the possibility remains theoretical, yet grounded in physics rather than imagination. If alignment of atmospheric drivers persisted with unusual steadiness, and if cold endured beyond ordinary spans, the threshold could be crossed. Depth and volume remain the principal guardians against that outcome, distributing stored heat across space and time. The inland seas carry within them both the capacity for widespread freezing and the resilience conferred by their scale, balancing potential against resistance in each unfolding winter. When a vast expanse of liquid freshwater transitions into ice, the change does not end at the shoreline. The transformation alters how energy moves between water and sky, adjusting regional balance in quiet but measurable ways. A frozen surface reflects far more sunlight than open water. Dark liquid absorbs incoming radiation, storing warmth that later moderates the air above. Ice, especially when capped with snow, returns much of that light back to the atmosphere. This shift in reflectivity, known as the albedo effect, reduces the amount of solar energy retained within the basin. As reflectivity increases, local cooling can intensify. With less absorbed sunlight, surface temperatures remain lower during daylight hours. The cooling may reinforce itself in subtle feedback loops. Colder air preserves ice longer. Extended ice cover maintains high albedo. Continued reflectivity limits warming. The process does not create endless decline, but it can sustain winter conditions beyond what a brief freeze might achieve. Reduced evaporation introduces another change. Open water continuously exchanges moisture with the atmosphere, even during cold months. When ice seals broad areas, that exchange diminishes sharply. With less vapor rising from the surface, atmospheric humidity declines in adjacent regions. This decrease influences cloud formation and precipitation patterns, particularly in zones typically fed by lake effect systems. Some downwind areas may observe reduced snowfall once ice becomes widespread, while others experience shifts in storm track behavior as surface temperature contrasts evolve. Snowpack, however, may increase during the earlier phase of freezing when partial ice cover coexists with persistent cold. As discussed before, open water can amplify snowfall under specific wind alignments. Once ice expands and limits further moisture supply, the snow that has already accumulated may linger longer because reduced solar absorption delays melting. Extended snow cover across surrounding land reinforces regional cooling by reflecting additional sunlight and insulating soil from milder air incursions. The hydrologic cycle adjusts accordingly. Lower evaporation from the lakes slightly decreases moisture contribution to winter precipitation totals in certain basins. Spring runoff patterns may respond to the combined timing of snowmelt and ice breakup. The interconnected system of water and atmosphere absorbs the effect gradually, each component responding according to its own scale. To lock up such a large fraction of surface freshwater is therefore not an isolated visual event. It shifts reflectivity, moderates heat exchange, influences humidity, and reshapes seasonal feedbacks across a broad geographic area. The inland seas function as climatic regulators in liquid form. When frozen, they regulate differently, returning more light to the sky and conserving what little heat remains beneath their pale, reflective surface. Winter alters not only what the eye perceives, but what the ear receives. When water moves freely, it carries a constant murmur, a low percussive rhythm of waves against shore, the soft collision of drifting surface ripples, the breath of wind tangled in motion. Once ice binds that motion, the soundscape changes with it. The transformation is immediate yet subtle, as if a layer of felt has been placed over the world. Solid ice conducts vibration differently than liquid water. Sound travels efficiently through dense, continuous material, often over surprising distances. A sharp crack caused by thermal contraction can resonate across miles, the energy moving swiftly through the frozen sheet. The tone is deeper and more metallic than open water, echoing briefly before dissolving into still air. These reports arrive without warning, separated by long intervals of near silence. In the absence of waves, the persistent background noise that usually masks smaller sounds recedes. Harbors no longer echo with repetitive surges. Shorelines rest without the repetitive cadence of breaking crests. Wind crossing a frozen expanse produces a flatter, more uniform whisper, unbroken by splash or spray. Footsteps on ice carry distinctly, each contact amplified beneath boots as vibrations disperse outward. Human perception responds keenly to this shift. People accustomed to winter storms rolling across open water often describe frozen seasons as unusually quiet, even when air temperatures remain severe. The visual vastness persists, yet auditory cues diminish. Without the dynamic interplay of water and wind, the environment feels suspended, as though motion itself has been reduced to a minimum. The mind registers the difference long before language forms around it. Historical journals from shoreline communities occasionally remark upon this altered atmosphere. Observers noted the peculiar stillness that accompanied heavy ice cover, contrasting it with the roar of unfrozen winters. Sailors writing from distant decades described nights when the lake lay silent beneath moonlight, interrupted only by distant booms as expanding ice shifted under pressure. Such accounts rarely dramatize the experience. Instead, they record it with understated surprise, aware that the usual soundtrack of the inland sea had withdrawn. Beneath the frozen surface, faint sounds continue, transmitted through solid medium rather than rolling water. Ice flexes with changing temperature, contracts under radiational cooling, and responds to subtle stress redistribution. Yet, these noises punctuate rather than fill the air. What remains between them is a broad quietness that stretches across horizon and shoreline alike. The silence of a frozen surface is therefore not emptiness, but transformation. Energy still moves, stress still redistributes, and life persists below. The difference lies in the way motion communicates, shifting from continuous murmur to intermittent resonance, leaving wide spaces of calm between each restrained note of winter. Above the cloud deck, instruments circle the planet with patient regularity, watching winter unfold in wavelengths invisible to the human eye. Where observers on shore once relied upon scattered reports and distant horizons, modern satellites render the entire basin at once, translating reflected light and emitted radiation into detailed maps of ice and open water. Each pass captures subtle differences in texture, temperature, and motion, assembling a continuous archive of seasonal change. Ice mapping technology begins with remote sensing, the collection of information without physical contact. Optical sensors detect variations in albedo, distinguishing bright ice from darker liquid surfaces when skies are clear. Microwave radiometers penetrate cloud cover, measuring the natural radiation emitted by Earth's surface and allowing analysts to estimate ice concentration regardless of weather. These tools transform raw signals into color coded composites that reveal coverage percentages across every basin. Infrared instruments add another dimension. By tracking surface temperature, they identify regions where open water persists within otherwise frozen expanses. Warmer patches appear distinctly against the cooler matrix of ice, offering early indication of leads, polynias, or areas where thinning has begun. Nighttime readings prove especially valuable as the absence of solar reflection allows thermal contrasts to stand out sharply. The result is a precise thermal portrait of the inland seas through the darkest months. Data collected from orbit feeds directly into predictive modeling systems. Numerical weather models ingest atmospheric conditions, surface temperatures, wind vectors, and historical patterns, projecting how ice may expand or retreat under forecast scenarios. Lake-specific models incorporate bathymetry and heat storage calculations, simulating interactions between water column temperature and surface flux. These projections do not replace observation, yet they extend it forward in time, offering probabilities for ice growth or breakup across coming days and weeks. The integration of satellite monitoring with buoy networks and coastal stations refines accuracy further. Measurements from floating sensors confirm surface temperatures and ice thickness in select locations, anchoring remote estimates to tangible values. Together, orbiting instruments and in situ observations create a layered understanding, one that spans scale from basin-wide coverage to localized detail. Through this synthesis, winter becomes measurable in near real time. Maps once compiled weeks after the fact now update daily, sometimes hourly, as new passes deliver data. Patterns that once seemed abrupt can be traced through gradual progression visible from space. The inland seas remain vast, yet they are no longer inscrutable. Silent, frozen surfaces send signals upward in reflected light and thermal radiation, and satellites gather those signals with steady attention, translating seasonal transformation into streams of data that deepen understanding of ice and atmosphere alike. When water hardens into a continuous plain, geography rearranges itself. Channels that once required ferries or long detours compress into straight lines across white expanse. What had been barrier becomes pathway, if only for a season. Under sufficient thickness, marked routes appear, staked with evergreen branches or reflective poles to guide travelers across what was recently open water. Temporary ice roads demand careful judgment. Before any crossing is declared usable, thickness must be measured repeatedly at multiple points. Clear, dense ice provides greater strength than layered formations riddled with trapped air. Vehicles advance slowly to reduce stress, maintaining distance to prevent concentrated loads. Even then, the road remains provisional, subject to subtle shifts in temperature, wind, and underlying currents. Each crossing reflects a negotiation between necessity and caution. Long before plowed tracks and modern gauges, indigenous communities understood winter as a season of altered movement. Frozen rivers and lakes offered direct access between settlements, hunting grounds, and trading partners. Travel by snowshoe and sled followed routes chosen for known currents and predictable thickness. Knowledge passed through generations identified safer corridors where depth and wind patterns favored consistent freezing. Winter landscapes were read not as obstacles, but as dynamic maps. Historical accounts from early European settlers describe similar adaptations. Once heavy ice secured harbors and bays, teams of horses hauled timber and goods across the surface. Markets once accessible only by boat reopened by sled. In certain winters, entire caravans traversed frozen stretches that would otherwise demand lengthy shoreline travel. These passages were rarely taken lightly. Diaries note careful probing ahead of each advance, listening for hollow echoes beneath the crust. The transformation from liquid corridor to frozen highway also shaped settlement patterns. Communities timed activities around freeze and thaw, anticipating weeks when direct routes shortened distances dramatically. Trade networks adjusted accordingly, expanding inland during months when waterborne transport paused. Even communication improved temporarily. Letters and supplies conveyed more directly across solidified surfaces. Such adaptations required intimate familiarity with the inland seas. Ice thickness varies with depth, current, and exposure, demanding local understanding rather than distant assumption. Snow cover may conceal weaknesses, and pressure ridges can create unexpected obstacles. Those who relied on these roads learned to interpret subtle signs, from surface texture to changes in tone underfoot. A frozen lake, therefore, represents more than meteorological curiosity. It is a shifting extension of the land, inviting passage while reminding travelers of its conditional nature. For a brief interval each winter, water yields to footstep and runner blade, weaving temporary connections across basins that will, with thaw, return to motion and reclaim their former boundaries. Change rarely announces itself in winter with thunder. Instead, it begins with a subtle softening. Sunlight lingers a little longer each afternoon, and the angle of its return carries more warmth than before. Beneath the frozen surface, stored energy slowly accumulates. Air temperatures fluctuate above and below freezing, introducing cycles of melt by day and refreeze by night. The rigid plane that once seemed immutable starts to weaken from within. Ice breakup follows when sustained warming overtakes structural strength. Meltwater gathers in shallow pools across the surface, darkening patches that absorb more sunlight and hasten local decay. Cracks widen along pressure seams formed months earlier, and gentle swells beneath the ice begin to flex the sheet. What had been a single expanse fractures into flows of varying size. Wind re-enters the conversation, driving these sections into one another with renewed momentum. When breakup accelerates rapidly, hazards emerge along shorelines and river outlets. Large flows pushed by persistent wind can pile against coastal structures, exerting lateral force that rivals winter compression. Channels choked by drifting ice may obstruct outflow from tributaries, raising water levels upstream. Temporary ice jams form where narrowing passages constrain movement, causing localized flooding until the blockage releases. The process is dynamic and often unpredictable, governed by the interplay of wind, current, and the evolving strength of the ice itself. Shoreline erosion becomes more pronounced during turbulent transitions. Freed from their frozen restraint, waves regain amplitude and strike coasts still saturated from thaw. Receding ice exposes unconsolidated sediments that had been stabilized through winter, allowing renewed mechanical action to reshape beaches and bluffs. Where protective ice once dampened wave energy, open water restores the full force of wind-driven motion. Spring storms arriving during this vulnerable interval can accelerate change. The transformation is not solely destructive. As ice disperses, light penetrates more deeply into the water column, stimulating biological activity that had persisted at subdued levels. Thermal stratification begins its gradual reformation, guided by increasing solar input and calmer conditions between storms. Migratory species respond to shifting cues of temperature and daylight, re-establishing seasonal patterns that link water to surrounding landscapes. Rapid thaw, therefore, represents both release and risk. Ice that accumulated over months yields within weeks, redistributing mass across the basin and along its margins. Flooded shorelines, rearranged sediments, and drifting flows testify to the energy stored in frozen form and suddenly set free. The inland sea, once restrained beneath winter's architecture, returns to movement, carrying forward the imprint of a season that briefly transformed its surface into solid ground before surrendering again to fluid motion. Duration shapes winter as much as depth or coverage. Some seasons freeze broadly, yet briefly, while others hold their grip far beyond expectation. In the historical archive of the Great Lakes, a handful of winters stand out not solely for how much ice formed, but for how long it remained. Records compiled from coastal stations, ship logs, and later satellite observations reveal stretches when extensive ice cover persisted for several consecutive months, delaying breakup well into the heart of spring. During the most prolonged freezes on record, large portions of certain lakes remained sealed from midwinter through late season transitions. Ice lingered across wide basins, resisting early thaws that in other years might have fractured it by late March. In those rare intervals, the cumulative number of days with high coverage reached exceptional totals, establishing benchmarks against which later seasons are measured. The exact ranking varies by lake, since each responds differently to depth, wind exposure, and heat storage, yet the overall impression is consistent. Winter, in those years, extended its authority without interruption. Multi-month coverage alters biological and chemical rhythms beneath the surface. Extended insulation reduces wind-driven mixing for longer periods, increasing reliance on oxygen reserves established before freeze-up. In deeper basins, the stability of cold, near 4 degrees Celsius water offers refuge, but in sheltered shallows, prolonged ice can stress aquatic communities. Light penetration remains suppressed, slowing photosynthesis and shifting energy flows towards stored organic matter. Fish adapt by further conserving movement, and plankton communities compress into resilient assemblages capable of enduring dim conditions. The shoreline environment responds as well. Snow accumulates on thickened ice, reinforcing reflectivity and slowing melt once daylight strengthens. River inflows encounter a persistent barrier at the lake margin, sometimes backing up until gradual warming opens outlets. Wetlands that would typically begin early seasonal transitions remain locked in suspended animation, awaiting breakup. Human activity adjusts quietly to extended freeze. Navigation seasons shorten, and maintenance operations shift into prolonged winter mode. Ice monitoring efforts intensify, tracking stability and thickness across months rather than weeks. For communities accustomed to mid-spring relief, the continued presence of solid surface can feel like a stretching of calendar time itself. Yet even the longest freeze carries within it the inevitability of change. Solar angles rise, atmospheric patterns realign, and stored energy beneath the ice begins its slow ascent. What distinguishes the longest recorded freezes is not permanence, but persistence. They demonstrate how the inland seas, though vast, can remain sealed for extraordinary spans when cold endures. In those years, duration becomes winter's defining feature, a steady extension of stillness across water that will eventually return to motion. Patterns become visible, Only when seasons are laid side by side, year after year, like pages in a long record of winter's handwriting. When viewed across decades, the Great Lakes reveal shifts that extend beyond any single freeze. Average air temperatures have gradually risen, and with that rise, the typical duration and extent of ice have trended downward in many analyses. The inland seas still freeze, sometimes dramatically, yet the baseline around which those events fluctuate has shifted. Reduced ice coverage in recent decades appears not as a uniform decline, but as a subtle recalibration. Some winters pass with wide expanses remaining open, their dark surfaces absorbing sunlight deep into February. Others surge unexpectedly toward high coverage when atmospheric patterns briefly align. This contrast underscores increased variability. Warmer global averages do not eliminate cold outbreaks. Rather, they alter the frequency and persistence with which cold can dominate. Climate change influences winter through multiple pathways. Higher mean temperatures reduce the likelihood that prolonged sub-freezing periods will endure without interruption. Earlier springs advance the timing of breakup, shortening the overall season of ice. Warmer autumns delay initial formation, narrowing the window during which freezing can progress. Even small increases in average temperature can tilt the balance in a system already governed by precise thresholds. Models projecting coming decades incorporate greenhouse gas scenarios, ocean temperature trends, and atmospheric circulation changes. Many simulations suggest that average ice coverage across the Great Lakes may continue to decline over time, with extreme high coverage winters becoming less common. Yet models also indicate that variability will persist. Occasional severe freezes remain possible under favorable oscillation phases, even in a warming climate. The interplay between long-term warming and short-term atmospheric patterns produces a landscape of risk and resilience intertwined. For ecosystems and communities, the lesson lies in adaptability. Reduced ice may alter evaporation rates, snowfall distribution, and shoreline dynamics. Shipping seasons could lengthen, while winter road access might become less reliable. Aquatic species accustomed to predictable ice duration may encounter shifting habitats. At the same time, the potential for abrupt cold seasons reminds planners that extremes have not vanished. Future winters will likely express a blend of gradual change and episodic intensity. The inland seas respond sensitively to atmospheric forcing, and that sensitivity ensures continued fluctuation even against a backdrop of rising averages. The record does not close with a single trend line. Instead, it expands, accommodating new data each year as ice forms, retreats, or lingers. In that unfolding pattern lies a broader understanding. The Great Lakes are dynamic systems, neither fixed in perpetual freeze nor immune to shifting climate. Their winters will continue to evolve, shaped by global forces and regional variability in concert. Probability rarely speaks in absolutes. It moves instead in ranges and return intervals, in shifting likelihoods shaped by forces larger than any single winter. When considering whether another season of near total ice could unfold, scientists turn to historical frequencies and atmospheric drivers rather than to singular memories. Extreme winters do not vanish from possibility simply because averages drift upward. They recede into lower probability while remaining within the bounds of physics. Return cycles offer one lens through which to view such events. By examining past decades, researchers estimate how often high coverage winters have occurred under varying climate conditions. The intervals are irregular. Some decades cluster with intense freezes, while others pass with only moderate ice. The distribution suggests that extreme cold seasons emerge when several atmospheric oscillations align simultaneously, reinforcing one another rather than canceling out. These alignments are rare, but rarity is not impossibility. Arctic amplification complicates the picture further. The polar region has warmed more rapidly than many mid latitude areas, reducing the long term contrast between pole and equator. This shift may weaken certain circulation patterns that historically confined frigid air to high latitudes. Some studies propose that diminished temperature gradients can encourage greater waviness in the jet stream, allowing occasional lobes of cold air to descend southward despite overall warming. The debate remains active within the scientific community, yet the central point endures. A warmer world does not preclude episodic cold. Forecasting such extremes carries inherent uncertainty. Seasonal outlooks can identify tendencies based on ocean temperatures, snow cover, and stratospheric conditions, yet precise outcomes depend on complex interactions unfolding weeks in advance. Small deviations in pressure placement or wind direction can alter trajectories of Arctic air masses significantly. As a result, long range forecasts express confidence in probabilities rather than guarantees. In practical terms, the chance that all lakes approach exceptional coverage again is lower than during colder baseline decades, but it remains measurable. A prolonged negative phase of the Arctic Oscillation, combined with favorable Pacific patterns and sustained clear skies, could recreate conditions conducive to widespread freezing. Each ingredient must persist long enough to overcome stored heat and latent energy within the water column. Thus, the question of recurrence rests not in speculation, but in statistical space. The inland seas continue to respond to atmospheric variability superimposed upon gradual warming trends. Extreme winters occupy a narrower corridor within that variability, yet the corridor remains open. The future holds fewer frequent freezes of historic scale, yet not an absolute barrier against their return, as probability bends but does not disappear in a changing climate. Climate expresses itself not only through extremes, but through quiet shifts in baseline. Across recent decades, average air temperatures around the Great Lakes have risen gradually, especially during winter months. The change is measured in degrees rather than dramatics, yet even modest increases alter the balance between water and ice. Freezing now begins later in many years, and breakup often arrives earlier, compressing the season during which solid cover can persist. Satellite records and coastal observations together show a general decline in average ice extent compared with colder periods of the 20th century. Some winters still produce widespread coverage when atmospheric alignment favors sustained cold, but the long term trajectory reveals fewer seasons reaching the highest historical percentages. Central basins that once froze more frequently now remain partially open in years that previously might have sealed more fully. The shift does not erase winter, yet it reshapes its expression. Warmer averages carry layered implications. With reduced ice cover, open water absorbs more sunlight during late winter and early spring, enhancing heat storage and influencing near-shore temperatures. Evaporation may increase during certain months, contributing additional moisture to passing weather systems and subtly modifying snowfall patterns. Shoreline communities observe changes in seasonal timing, from altered snow accumulation to variations in spring runoff. Shipping benefits in specific ways from shorter ice seasons. Navigation windows lengthen, reducing the need for extensive ice-breaking operations and allowing freight movement earlier in spring and later into autumn. Economic planning adjusts around these extended intervals of open water. Yet increased variability requires flexibility, since occasional severe winters can still interrupt routes unexpectedly. Ecological responses unfold more gradually. Many aquatic species rely upon predictable seasonal cues tied to temperature and ice duration. Reduced ice may influence spawning timing, nutrient cycling, and the balance between cold adapted and warm tolerant organisms. Earlier stratification in spring can alter oxygen distribution and productivity patterns. The interconnected food web adjusts to these changes, sometimes subtly, sometimes with cascading effects that researchers continue to monitor. Shoreline processes also evolve. Without persistent ice to buffer wave action, winter storms may reach coasts more frequently, enhancing erosion in vulnerable areas. Sediment transport patterns shift as open water persists during months once dominated by solid cover. Infrastructure designed with historical freeze patterns in mind may require adaptation as those patterns evolve. The Great Lakes therefore exist within a climate story that is neither static nor singular. Warmer averages, reduced ice cover, and ongoing variability interact to reshape winter's character. The inland seas remain vast and dynamic, yet the cadence of freezing and thawing reflects a broader transformation occurring across the planet, measured quietly in the timing and extent of ice each passing year. There are moments when vast systems fall into balance so precisely that motion itself seems to hesitate. Air descends from high latitudes carrying unusual persistence. Winds align in steady direction. Stored warmth releases faster than it can be replenished. Energy drains from the surface layer day after day, each hour subtracting more than it returns. Nothing in the sequence is theatrical on its own. Yet together, cold, circulation, and loss form a narrow corridor through which even an inland sea can pass. Water that once held the memory of summer gradually relinquishes it. Mixing slows as temperatures approach equilibrium from top to bottom. Heat that had been distributed through depth rises and disperses into the atmosphere. When thresholds are crossed, phase begins to change. Molecules arrange into crystalline order, latent energy slips quietly away. The transformation requires vast removal of stored warmth, an accounting measured not in a single storm, but in weeks of cumulative exchange. From above, the surface brightens. Bands of white expand outward across basins that span horizons. Shorelines knit together, channels tighten, open expanses contract into darker pools ringed by pale geometry. The scale is almost difficult to hold in the mind, because the expanse involved once behaved like open ocean, generating waves, weather, and internal tides. That such breadth can shift state at all feels improbable until physics is allowed its patience. Massive systems do not change because they are fragile, they change because they are interconnected. Atmosphere and water share energy constantly, trading it through wind, radiation, and evaporation. When external forcing persists in one direction long enough, even great reservoirs respond. Thermal inertia slows the transition but does not prevent it. In that sense, magnitude offers resistance, yet also amplifies outcome, because when a body this large approaches uniform conditions, the resulting stillness extends across distances once defined by motion. What nearly occurred in those rare alignments was not a theatrical freezing at once, but a steady advance toward continuity. Separate sheets approach one another, gaps narrow, currents diminish beneath thickening cover. The inland sea, known for storms and restless horizons, approaches a kind of suspended breath. Ships that once traced its surface pause. Waves that once carried sound and momentum yield to muted resonance across solid plains. Stillness at this scale does not suggest permanence. It reveals capacity. It shows that even immense systems respond to sustained pressure from their surroundings. The Earth remains dynamic not because it is unchanging, but because it is perpetually negotiating energy across air, water, and land. When an inland sea goes still, the quiet does not signal fragility. It offers perspective, a reminder of proportion, of thresholds crossed through accumulated exchange, and of the remarkable balance that allows motion to return when the equilibrium gently shifts once more.